Valence bond theory and molecular orbital theory by myself and Dathan White. Action.
Okay, in order to better understand the valence bond theory, we're going to look at homework number 17 in chapter 14. It talks about diatomic fluorine. So come a little closer. I'll show you a few things. So here we have two fluorine atoms that are going to be connected by this bond. See, this would be a normal F2 diatomic. Okay, so these diatomic atoms satisfy the octet rule because we have 8 electrons in each fluorine. And if we wanted to look at, say, F2 minus, we might have some problems because we're gonna get an extra electron and I'm not really sure where that's gonna go.
Alright, as Dathan showed us, valence bond theory is fine for molecules like F2. However, when we have something like F2 minus, like we do in our homework, we saw that valence bond theory wasn't sufficient enough. Therefore, we need a better way of representing this molecule, and the way we're going to do that is through molecular orbital theory. Alright, so as you can see here, I have drawn the molecular orbital diagram for an F2 molecule. On the left, we just have a single axis of increasing energy, and here we have our 2s orbitals and our 2p orbitals. Alright, so fluorine has 7 valence electrons in each one with a total of 14. So let's go ahead and fill these into their normal orbitals before they're bonded. That's 3, 4, 5, 6, and 7. And over here we have 1, 2, 3, 4, 5, 6, and 7. And sorry, these are opposite spin. Alright, so now that we have them in here, let's go ahead and fill in our hybrid orbitals. We'll start at the lowest energy level and work our way up. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And there is all 14 of the electrons represented. Alright, so now, this doesn't really tell us a whole lot yet. So we have to figure out which ones of these are the bonding orbitals and which ones are the anti-bonding orbitals. And so this is our sigma orbital, and we'll call this sigma G, and we'll call this one sigma U. And in this case, sigma U is our anti-bonding orbital, which we'll talk about in a little bit, why this is our anti-bonding orbital. Alright, and so we have sigma G, and these both are pi U, and then this one now is pi G, and here we have sigma U. Now remember, we have F2 minus now, so we actually have an extra electron up there. And so that is how this is a better representation than the valence bond theory, because we now have a place for that electron to go. Alright, so you're probably really confused about what this U and G means. Well, G is actually Gerada and U is Ungerada, and I'll now throw it over to Dathan to explain this to you.
100. Oh, didn't see you there. Alright, so if we want to talk about Gerada versus Ungerada, we first have to talk about the sigma and the pi orbitals. So what sigma is going to look like, it's going to be a linear line. When you're looking at it from the side, it's going to look like a circle. And then the pi orbital is going to look like this. And when you're looking at it from the side, you're going to get the classic dumbbell shape. Okay, so now let's look at the Gerada in the sigma orbital. We have 2 sigma orbitals. When you put them together, we have a singular bonding orbital. And the reason that this one is Gerada is because we start at one end of the molecule and we have a negative charge. When we go to the other end, we still have a negative charge. So that's called Gerada symmetry. And this is an example of an Ungerada. And we have antibonding here because these 2 sigma bondings are out of phase. And we have, on this end of the molecule, we have a positive charge. And when you cross the molecule, we end up on the negative side. So when they change, we have Ungerada.
Alright, so now let's talk about the pi orbitals. pi orbitals are going to line up something like this. As you can see here, these pi orbitals are in phase because you have positive, positive next to each other and negative, negative next to each other. However, unlike the sigma orbitals, when they are a bonding orbital, this is actually not Garada. Because as you can see, if you go from one side of the molecule to the other, you're actually going from negative to positive, making this an Garada symmetry, even though it is a bonding orbital. So now let's take a look at what it looks like if it's out of phase. If you flip these around, now we have our anti-bonding orbital, meaning because these are now out of phase, going from positive to negative. However, this is actually Garada symmetry, because if you go from one side of the molecule to the other, you're going from the same, you're not changing signs. As you can see here, going from the positive to the positive. Hold on, can you hold for a second? Alright, so now that we described the Garada and Garada symmetries, let's go take a look at our molecular orbital diagram and investigate it further. Alright, so now that we have a better understanding of our bonding and anti-bonding orbitals, as well as our Garada and Garada symmetries, let's take a look at another important aspect of molecular orbital diagrams, and that is bond order. And I'll write the equation here for bond order, BO. Oh, we're good. And that equals the number of bonding electrons minus the number of anti-bonding electrons over 2. Now, for F2 minus, we can see that we have 1, 2, 3, 4, 5, 6 bonding electrons minus 1, 2, 3, 4, 5 anti-bonding electrons. And this is all over 2. That gives us a bond order of 1/2. Alright, so we have our bond order of 1/2 on F2 minus. So what does bond order tell us? Bond order tells us the stability of a bond. Basically, the higher the bond order, the more stable the bond is. As we can see, F2 minus is relatively unstable because it has a bond order less than 1. So what if we actually had F2 instead of F2 minus? Or just fluorine. So now we have a bond order of 1, making this a much more stable bond than the F2 minus. The third example in the homework is actually F2 plus, which we will then take away another anti-bonding electron, making our bond order now 1 1/2. So as you can see, F2 minus, the least stable bond, F2 the next one, and F2 plus is actually the most stable or the strongest bond from this bond order, which makes sense because it has the least amount of anti-bonding electrons.
Okay, another reason why molecular orbital theory is more informative than valence bond theory is that it is a way of checking paramagnetism. And what paramagnetism is, what it shows a net spin of plus or minus 1/2. For example, this F2 minus structure, we have this one unpaired electron, which gives us this spin, but if we take it away, in the F2, we would get a diamagnetic, and that would be a repulsion to magnetic fields, and the paramagnetic is it attracts magnetic fields.
We just want to thank you guys for watching our video on homework number 17 and concept valence bond theory and molecular orbital theory. I hope we helped you guys out.
Good luck on finals, crazy kids.
1! Come on! You can do it! You can do it! Get those p orbitals! Get those p orbitals!